Hello and welcome to my YouTube channel. Today I'm going to teach you, I'm going to make you understand the important topic, one of the human genetic disorder, and that's called hemophilia or bleeders disease. What is hemophilia? Do you know? Sometimes any person whose blood gets exposed to outside environment, it does not clot within that specific time, which is normal for a human being. The blood gets clotted lately, or it does not get clotted. Such a disease, where blood takes a time to get clotted, is called hemophilia or bleeders disease. It's a sex-linked recessive trait which is carried from one family to another, means from parents to first filial generations. So let us take this topic, important topic, which is in your syllabus for exams. So let us have it. So one of human genetic disorder is hemophilia. Hemophilia. Now, what is hemophilia? It is exactly one of the kind of human genetic disorder. So it is human genetic disorder. There are many human genetic disorder. These were discovered after Mendelism, who fixed his traits with different chromosomes. The researchers go on to move to genes and find that there are genetic disorders inside humans, and a lot of them have been discovered, like sickle cell anemia, color blindness, etc. Now, human genetic disorder, as I said, it is sex-linked recessive trait. It is sex-linked recessive trait. So that means it's found on sex chromosomes. Like we have 222 set a pair of autosomes equivalent to 44. Then we have X and Y, or X, there is sex chromosomes, allosomes. These equal to 2, total equaling 646. So this hemophilia is found in sex chromosome. It's located on sex chromosome and not on Y. It's X-linked. It's actually X-linked. So it's found on X chromosome. Very important, it's found on X chromosome. It's not Y-linked. It's not found on Y chromosome, but it's found on X chromosome. Now, it's called bleeders disease. It was discovered by John Otto way back in 1803 AD. This is called bleeders disease. Bleeders disease, because once blood gets exposed, it takes very much of time to get healed, to get clotted. So there is lack of clotting, and thus it gets a lot of problems. The gene is carried through X chromosomes. So what is the problem actually? The problem is in these individuals who have hemophilia, they lack the factor which is called plasma thromboplastin, plasma thromboplastin, or factor 9th. So that's why it's called hemophilia B. Hemophilia B, or Christmas disease. It's called Christmas disease. So this is one way this factor is lacking. Or there is one more problem. There is a lack of anti-hemophilia globulin protein. Anti-hemophilia globulin is lacking, or it's called factor. It's called factor 8. Okay, so that's why it's called hemophilia B, A. Hemophilia A. So remember these two. It is plasma thromboplastin is lacking, which is also called factor 9. This is called, thus this is hemophilia B. Or called Christmas disease. Sometimes question is asked, what is Christmas disease? It is hemophilia E. It's not hemophilia. It's hemophilia B. It's not hemophilia A. When anti-hemophilia globulin is lacking, which is called a factor 8, then it's called hemophilia A. So the first discovered in it is found that it goes through into British Crown, carried in British Crown through Queen Victoria, how exactly it was discovered, but it originated long before that in human race. So it is very important to know the crossings, the genetics. As you know how this disease is carried and what are the programs of this disease, how it can be forecasted, why it is found. So is found on X, so we can write XH means hemophiliac X. Another X without H is normal X. So this is normal X. This is hemophilic X. Okay. This X is having a gene. This X is the as I said, the thromboplastin, the factor 9 or factor 8 producing genes, they are not found in this X. They are absent. Okay, they are absent in this, but they are present in this. So this normal X, this hemophilic X. So there is actually a lack of factor, lack of some factors which help in clotting. Based on those factors, it can be hemophilia A or B. B1 is hemophilia B, is called a Christmas disease. Now, if we see the crosses, let us take the crosses. That's more important. And that's what exactly in examination will be asked. If there is a normal female, it is crossed with these are parents. The first generation will be first filial, F1, first filial generation. If X, so this is normal female, is crossed with hemophilic man. You know, man is always hemizygous because it has only one X. So woman can be carrier woman. Carrier woman is this is carrier woman, this is normal woman, this is hemophilic woman having both the X's affected. So this is hemophilic woman, hemophilic, this is normal, and this is carrier woman which carries this to next generation. But in case of man, this is normal man, this is hemophilic man. There is no carrier man, because once the man is affected, it has one X. When it is affected, it becomes hemophilic man, and this is hemophilic man. There is no carrier man. How can there be a carrier? Because it is completely either hemophilic or normal, because it is homozygous. There is only one X chromosome. So on the basis of this, we can show here it. This is hemophilic man. Hemophilic man. It is crossed with normal woman. So what will be produced? This X, if we took this X meeting with this one, is meeting this one, we will get a hemophilic. This is carrier daughter. So we will get carrier daughter, carrier D. If we cross this with this one, we will get again carrier daughter. Okay, so all the daughters will be carrier. If we cross this X with Y, we'll get X and Y, normal male. If we cross this X with Y, we will again get normal male. So that means in this situation, all daughters will be carrier and all the sons produced, they will be normal sons. Taking the second condition. Now, if we take another example where man is normal but female is carrier. This is carrier female versus this is normal man. The cross of this X with this X will produce carrier daughter. Cross of this X with this X will produce normal daughter. So this is carrier daughter, this is normal daughter. And this X with Y, hemophilic man, hemophilic son. With this X, with this Y, normal son, X and Y. So in this case, if we have a carrier mother, half daughters will be carrier, half daughters will be normal. Similarly, all the sons will be hemophilic. No, not all. Half the sons will be hemophilic because there is no carrier son or male, and half of sons will be normal. We take another example. By crossing carrier woman with hemophilic man, what will happen? This X will form hemophilic daughter, but this daughter will die before birth, dies before birth. This X with this X will produce carrier daughter, and this X with this Y, hemophilic man. This X with this Y, normal man. So the half sons will be normal, half sons will be hemophilic, and all daughters which are there will be carrier, because half the daughters which are hemophilic, they will die before birth. There will no daughter at all. So these become adult daughters. The adults will be, from adults we will be normal male, and then hemophilic male, carrier daughter, and all the hemophilic daughters they will not reach maturity, they will not go on to get married. So always we cannot find, it's very difficult or it's impossible to have a mother, to have a female which is hemophilic female, because that female will not go on to become adult, become mature, so that we can prepare her for marriage, because that daughter will die before birth. So there will be no hemophilic woman present. So we cannot cross hemophilic woman with any male. We can only cross either carrier woman, or we can cross normal woman with hemophilic man or normal man. So man is homozygous. Why didn't this man die before birth? Because it has another chromosome which is heterochromosome. The problem of bleeding will be there in hemophilic man, but it will not die, because why? The exactly counter pair will create such a situation that the death will be stopped. But in case of this female, when this gene is lacking, the gene is again here lacking, it will cause a lot of problem in protein synthesis, and other things related problems will occur with the amplification of problems, with the channeling and making up different problems to come together. The female dies, she cannot live, she cannot it's difficult that she'll be born. So it's definitely, so you can cross anyone with any way you can find. So with this concept, the question one of the question comes that comes from these crosses. If we cross this with this, how many daughters will be there? But you remember one thing, that this question is asked that if we cross normal, this carrier woman with hemophilic man, how many daughters will be there? Half of the daughters will be carrier, but half of the daughters will not be there, they will die. So we can write, she cannot produce hemophilic daughters because they will die before birth. So this cross can't be there. We can't make this kind of a cross, because you will not find this female anywhere. Okay. Now this is one of the important example of a bleeder's disease or hemophilia. The normal time taken for blood coagulation, clotting, it's affected, it's not that. With this, I hope must have understood the concept of hemophilia, bleeder's disease. And till next lecture, thank you.